Alrighty, it is 8. So I am Dr. Matthew Hartman. My office is upstairs in Neptune 211, although most of you probably won't be allowed to actually go up in there. I do have office hours Monday, Wednesday from 12:30 to 5, and Friday from 12:30 to 2. All of my office hours will be held via Zoom. And I'll put that information on our course's webpage as soon as I have access to it. My email address is my last name at lawtech.edu, and there's my office phone number, but I'm never in there, so you can try calling and leave a message, and maybe I'll respond. Emails generally work. I'm required to let you know that in the event of a disaster or other emergency, such as a university closure like we faced last spring, the class will continue via Moodle and Zoom, and all that kind of things. All right. So what we're going to be doing in this class is studying effectively PN junctions in their various forms. We're going to start with diodes and diode-based circuits, then move along to BJTs or bipolar junction transistors, and then finish things up with MOSFETs or metal oxide semiconductor field effect transistors. We're going to learn the basics of all of these, then we're going to analyze circuits that contain them, and then we're going to design amplifier circuits that utilize these. So it's a lot of stuff about PN junctions and their applications within the field of electrical engineering. Our textbook is Fundamentals of Microelectronics, 2nd edition by Bazad Razavi. He's written several textbooks on this and analog electronic design and stuff like that, so I really like this textbook. Let's see, disability disclosure. If you need testing accommodations or anything like that, go to the Office of Disability Services. Phone number's also there. Class attendance. This is officially, we will adhere to the guidelines for class attendance found in Chapter 3 of the University Catalog, blah, blah, blah. Unofficially, you're adults. You can come and go as you please. I will be running a concurrent Zoom session for all of our class meetings, meaning that if you choose not to attend in person, which I personally don't think is a particularly good idea, but you're an adult and you can make that decision for yourself, you can attend all of our class meetings other than the exams online, and I won't in any way, shape, or form hold that against you. It'll just be harder for you to interact with me and all that kind of good stuff. I am recording all of the Zoom meetings as well, so that I'll post them on my YouTube channel, usually within a couple of days of the class meeting itself, so that if you have to miss because you're quarantining or you just really don't feel like putting pants on that day or waking up for an 8 a.m. class or something like that, all the material will be archived online too. So any questions regarding the actual class attendance policy of you can kind of do whatever you want as long as you don't fail. All right. Academic misconduct. Bunch of words from the bulletin, generally speaking. Don't cheat and be less of a dick than I am, and we'll be good. Homework. All of the homework in this class is done on WebWork. It's already set up. So like your first homework set opens up immediately after this class and is due by 7:30 a.m. on next Monday. I don't know why Dr. Vitari is making all the homeworks due so crazy early in the morning, but that's his bag of cats, and I don't feel like arguing. So it is what it is. So you'll have the exact same homework problems and all that kind of good stuff as the other sections. Quizzes. I reserve the right to give a quiz if I feel like. So if you guys are slacking off and goofing off, I might be a jerk and be like, hey, I'm going to try to tank your grade just because I'm feeling ornery today. Projects. There's going to be 3 projects in this class. The projects are to be completed in groups of 3 students. Right now, there are only 20 students enrolled in this class. So one group will have only 2 students, unless we get some adding and dropping and shifting and all that kind of stuff. The projects will be based on real engineering problems where you'll be designing something to a specified set of criteria from a proposed customer, and you will be required to both design and simulate your solution. Let's see, there are 3 exams. All exams are closed book, closed notes. Says no makeup exams will be permitted unless approval is approved from the instructor, blah, blah, blah. COVID rules apply, meaning if you're under quarantine, I can't force you to come here to take the test. I'll have to provide an online version and all that kind of stuff. If your symptoms are so bad that you are, in the hospital or something like I was at the beginning of last quarter, then obviously I can't make you take the test on that day. We'll have to accommodate you within reason and all that kind of stuff. What I don't want to see is something that I saw last quarter in Circuits 1 of students just never showing up to class, being wildly unprepared, and then, oh shit, on the test day, I somehow came up with symptoms. That kind of stuff pisses me off. Just because, like I said, I've had it. It was a very unpleasant experience, and anybody that would joke about that or use it to their advantage disgusts me, to put it bluntly. So if you're going to claim that you have COVID, you better fake it real, real good, or actually have it. All right. The grading of this class is as follows. The homework and quizzes are 10% of your grade. Each exam is 24%, and each of the projects is 6%. The grade scale, 100 to 90% is an A, and 89.99 is a B, meaning I don't care. If you want to make an A in this class, you got to earn it. Standard 10-point scales. All right, syllabus changes. I don't think anything's going to change, but if it does, I reserve the right to do so, and I'll let you know. One thing I know for a fact that will be changed on the syllabus per se is after today, I'll be putting up a tentative course schedule after Dr. Bakari and I have a chance to nail down the test dates and all that kind of stuff. But right now, it looks like your first test would be on the day you get back from the holiday break, and that's even too much of a dick move for me. So I'd like to push it back at least one class meeting so that you don't show up at your first day back in classes and have to suffer through an electronic test. That's just too dang mean. All right, and then other boilerplate COVID stuff that should be on every syllabus that you get until this is over. One of the important things is this paragraph right here. So for a student who is exposed, you need to contact Miss Stacy Gilbert, whose email address is right here. Let her know. She will get in contact and place you with the SRT. I think that's the strategic response team and all that kind of stuff. And we'll work with getting you back on campus in a safe way and all that kind of jazz. And we'll work with all your professors to make sure your accommodations are met. All right, any questions regarding the syllabus? Hopefully fairly boilerplate stuff. All right, so for better or for worse, you guys have me for this class. This is my first time teaching this class at an undergraduate level. So I'm going to try to not be a crazy tyrant and make you guys learn all of the semiconductor physics and all that kind of stuff that I would cover when I taught this effectively at a graduate level. But I am probably going to add more of that material to this class than Dr. Bakari does, because I find it to be useful to help you understand really what's going on inside these little chunks of silicon and stuff like that. So if I ever get to where I'm talking at a much higher level than you guys are able to understand, please stop me and say, hey, tone it down and let's get back on track, okay? Because that's definitely a possibility. So today, all we're going to talk about is a little bit on linearity and nonlinearity, which is a topic that I cover in actually my Circuits 1 class, and it's a topic that you guys are going to be covering in your ELEN 321 class, probably later today, to some extent. So, got on my nuts, making my face sweat. All right, want to use blue. So let's see, can people actually see that? Let's start there. You guys in the back can see it. So that's an appropriate size. All right, I just want to make sure. So let's say that we have a black box system. And this black box system has a transfer function, h of x. And so what that means is that this system, it could be a single component or it could be a network of electrical components, is acting on some input signal. We're going to put the inputs on the left-hand side. So let's say that we have maybe an input signal x1 of t. This could be a current or voltage. And there might be multiple inputs. So let's call this guy x2 of t. And we're going to observe some output signal y1 of t and y2 of t. So what this network is doing is it's acting on signal x1, which might be a voltage, and it is converting it to some output signal y1 of t, which might be a voltage or current. So for instance, if this were a resistor, our input signal might be a current and our output signal would be the voltage. The transfer function would then simply be the resistor value, because we know that the current voltage relationship for a resistor is governed by Ohm's law. V is equal to I times R. So if V is the output, I is the input, R is the transfer function of the system. Okay? What I'm describing here is just a generic system that could be composed of resistors, capacitors, inductors, diodes, et cetera, blah, 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 all that kind of stuff. If we have some input x1 of t, our system acts on it, giving us an output y1 of t. And for an input x2 of t, our system acts on it and gives us an output of y2 of t. If this system is linear, that is not an L. The system response, or the output, must satisfy the following equation. H, our transfer function, acting on alpha times x1 of t plus beta times x2 of t will be equal to alpha y1 of t plus beta y2 of t. Now, this is a fairly complicated looking mathematical expression here, but it really can be boiled down into two distinct properties that a circuit, network, or component must satisfy in order to be considered linear. And those two properties are the additivity property and the homogeneity or scaling property. And we're going to talk about both of those. So the additivity property states, if several independent inputs are used to excite a system, the total response due to all of these excitations can be determined by considering each input separately while assuming all other inputs to be zero. This is nothing more than the superposition principle you guys learned in circuits 1, okay? So if I have my black box network, and I input, so this, here's its transfer function h of x. I input a signal x1 of t, I output a signal y1 of t, such that this guy is governed by the equation h acting on x1 of t is equal to y1 of t. And I take that exact same black box network and I apply a different input. And get an output y2 of t. So I can write the characteristic equation for this guy is h acting on x2 of t gives us an output of y2 of t. If the system obeys the additivity property, then if I apply both inputs simultaneously, I should observe that the system is governed by this equation. So if h of x acts on both inputs simultaneously, my output should simply be the sum of my outputs of each excitation function acting alone. So if I apply an input x1 to my system and get an output of y1, I take my same system and apply a different input and I get a different output. If I apply both of those inputs, my output should just be the sum of the outputs caused by each of the excitation occurring by themselves. And this is, again, exactly what you guys did using superposition in your circuits 1 and circuits 2, and I don't know if you guys use it in circuits 3 at all. But you turned off one voltage source and saw what the current or voltage somewhere else in the equation was, then you turned on another source, and then you added the results together. This is exactly that, but in a generalized sense. Okay. So that's the additivity property. The homogeneity property did I put property up here? No. Or scaling says if an independent input is used to excite a system, scaling that input by an arbitrary factor of alpha or some scaling factor causes the output to scale by the same amount. So if I have my black box network, I apply an input x1 of t, I get an output y1 of t. If I take that same black box network and I apply an input alpha x1 of t, if it obeys the homogeneity property, then my output should simply be alpha y1 of t. And we again saw this in circuits 1. So if I apply a 5-volt source to a 10 ohm resistor, so a 5 volts is my input, to a 10 ohm resistor, my output, I of t, would be what? So 5 volts across a 10 ohm resistor generates what current? half an amp, right? If I scale my input voltage by a factor of 2, putting 10 volts across that same 10 ohm resistor, what happens to my output? It scales by a factor of 2 to give me 1 amp. That's all this homogeneity thing means, okay? So a linear circuit network component is just one in which the homogeneity property and the additivity property apply simultaneously. So let's formalize that, all right? How much? Okay, next page. Examples of linear circuit elements. So let's start with a resistor. And again, we did all of this in circuits 1. But resistors are governed by Ohm's law. V is equal to R times I. So I'm going to say that our response is the voltage and our input is the current. So I could write an equation. V1 of t is equal to R times I1 of t. Let's call this guy equation 1. And V2 of t is equal to R times I2 of t. Call this guy equation 2. So these are my input-output relationships for 2 distinct input signals, one being I1 of t and the other being I2 of t. We're going to test for linearity here, okay? So what I'm going to do to test is I'm going to scale equation 1 by a factor of alpha and scale equation 2 by a factor of beta, and then add the results together and see if what it looks like is my original characteristic equation, Ohm's law. So I would have alpha V1 of t plus beta V2 of t is equal to R times alpha I1 of t plus R beta I2 of t, and I can collect like terms and I can see that this equation is the exact same thing as my characteristic equation, Ohm's law, where V of t is alpha V1 plus beta V2, and I of t is alpha I1 plus beta I2. So if I substituted this for V1, or excuse me, this for V of t and this for I of t into my original equation, I get the exact output that I get here. So we can say that resistors are an example of a linear circuit element, okay? And again, that shouldn't be any huge revelation because we just talked about simple examples that proved it just a couple of moments ago. Now we're going to talk about inductors and capacitors and their linearity. And this was never remotely addressed actually in your circuits 1 class or circuits 2 class or anything like that. We just kind of assumed they work. So we're going to prove it now. So for an inductor, our voltage current relationship, V of t is governed by V of t is equal to L di by dt, right? So what we're effectively going to prove is that the derivative operation is a linear operation. So let's say that we have an output V1 of t from a corresponding input L multiplied by d I1 by dt. Call this guy equation 3. And our output V2 is because of an input L times di2 dt. We're going to do the exact same thing. We're going to scale equation 3 by alpha, scale equation 4 by beta, add them together, and see if it looks like our characteristic equation. So alpha V1 plus beta V2 is equal to L d by dt alpha I1 plus L d by dt beta I2. Those brackets should be the same size. All right. So let me ask you guys a question. Can I do this operation? So all I've done here is instead of saying I'm taking the derivative of each of the signals individually, I'm now taking the derivative of the sum of the scaled signals. Is there anything mathematically wrong with that? Not at all, right? So the derivative of x squared plus the derivative of x is the same as the derivative of x squared plus x, right? There's no mathematical fouls or anything like that going on. So I can see then that this equation is the exact same thing as my characteristic equation, where v of t is alpha v1 plus beta v2, and I of t is alpha I1 plus beta I2, just like in our resistor case, right? So this guy is linear as well. So let me write that here. So under the condition, v of t is equal to alpha v1 plus beta v2, and our total input is alpha I1 plus beta I2. All right, I think I got enough room for capacitors here. All righty, so for a capacitor, our governing equation is the voltage is 1 divided by C times the integral from negative infinity to T times I of tau d tau, where tau is just a dummy variable for time here, nothing fancy going on. And explicitly setting my derivative, or excuse me, my integral limits from negative infinity to t to account for not having a initial condition on this thing. So we're assuming that infinitely long ago, way in the deep dark past, our capacitor didn't have a voltage drop over it. So it had 0 energy. So that's all those limits of integration. So if I have an input signal I1, then I should get an output V1 is equal to 1 by C, negative infinity and if I have a different current, I'll get this relationship. Call this guy 5, call this guy 6, And again, I'm going to do the exact same thing. I'm going to scale equation 5 by alpha, scale equation 6 by beta, add them together, and see if it looks like my original equation. So that would give me alpha V1 plus beta V2 is equal to one over C integral alpha I1 plus 1 over C integral beta I2, that should be tau, not T. And I can effectively group like terms again, and I'll have 1 by C integral Is there anything wrong with that mathematical operation? So instead of taking the integral of each individual scaled signal, I'm taking the integral of the sum of the scaled signals. Anything wrong with that? No, right? So again, this guy is then linear, because if our input current is alpha I1 plus beta I2, we get an output voltage of alpha V1 plus beta V2. Kind of running out of room here, so let's put it here. So V of t is alpha V1 plus beta V2, and I of t is alpha I1 plus beta I2. So we have proven that resistors, inductors, and capacitors all behave linearly. Now, you may be asking yourself, well, does everything behave linearly? And so I'd like to show you what I consider to be a hilarious example of nonlinearity. So let's say that we have an input-output relationship. Y of t is equal to x plus b. What is this equation? A linear equation, right? Linear meaning it is the equation that tells us how to plot a straight line in a two-dimensional coordinate system, all right? So if I have some input x1, I could say that my output y1 of t would be caused by m x1 of t plus b, and similarly y2 would be m x2 plus b. So I'm going to do the exact same thing I did previously. I'm going to scale my first equation by alpha, and I want to be clear here. The homogeneity property tells me to scale explicitly. If I scale my input, I get to scale my output. So I'm going to scale equation, the top one by alpha and the bottom one by beta. So that would give me, and add them together. So I would have alpha y1 plus beta y2 is equal to m alpha x1 plus b plus m beta x2 plus b is equal to m alpha x1 plus beta x2 plus 2b. So is what we know to be a linear equation linear? It's not, because of that DC offset effectively, or the y-intercept of b. That's what's making it a nonlinear relationship. So the one thing that we've been taught is a linear equation, this, since probably the 4th grade, is actually nonlinear from a signals and systems perspective. what we're going to be talking about in this class. Okay, so we will say then that a linear circuit is any circuit consisting only of linear passive elements linear dependent sources and independent sources. All right, so effectively every circuit that we analyzed in circuits 1, circuits 2, and I don't know exactly what you guys analyzed in circuits 3 last quarter, but I'm willing to bet that they were all linear circuits as well. And I can't say actually all the circuits in circuit 2 because we talked about nonlinearity and the saturation distortion. When in circuits 2 at the very beginning of the class, we talk about how the output of the amplifier cannot exceed effectively the supply voltages and all that kind of stuff. Anything outside of that range is nonlinear behavior. So technically we have analyzed a couple of nonlinear circuits back in circuit 2. But anyway, here's our fundamental definition of a linear circuit. Now let's talk about nonlinearity and electronics, all right? And why we're talking about all this stuff. We have a diode. Our diode current is given by IS, which is the reverse bias saturation current, something we'll talk about later, E to the VD divided by VT, where VT is the thermal voltage, again, something we'll talk about in considerable depth later, but at room temperature, it's 26 millivolts. This is inherently a nonlinear relationship. It's exponential. We can literally see that it is nonlinear, okay? PN junctions are diodes. Bipolar junction transistors are effectively two diodes stacked together. MOSFETs are similar to two diodes stacked together, except they have gate control. All three of the components that we're going to be dealing with in depth in this class behave non-linearly. So what that means is that we can't use Laplace and Fourier transforms to simplify anything. We can't apply Thevenin and Norton's theorems because they explicitly say that for any linear two-port network, blah, blah, blah. So that's out as well. The only things that we can really rely on are Kirchhoff's voltage law and Kirchhoff's current law, because those are the law of conservation of energy and the law of conservation of charge as applied to circuits. Those are fundamental physics rules, so we can't get past them. But an awful lot of the circuit analysis techniques that we have learned to analyze circuits to this point have to get thrown out of the window because we're going to be dealing with nonlinear circuits. So what we're going to be doing is we're going to be using more advanced numerical methods to directly solve these. We're going to be idealizing or simplifying the behavior of our elements so that it's approximately linear under certain conditions. And we are also going to be doing small signal analysis, which is effectively meaning we're going to look at these circuit elements at a very specific operating points and subtle variations above and below that operating point to see how they behave. Because if we look at one part of its operational curve, we can get a linear a linear approximation of what's going on. So that's all that I have for today. So we've talked an awful lot about linearity and how we're effectively just going to throw it all out the damn window and do something else starting on Friday. So I'm going to pass this around real quick because I forgot to do it at the beginning of class. It's literally a blank sheet of paper. I would just like you to sign it for the roll. Once you do that, you're free to leave.